Here we'll introduce the cross product. It's a way to combine two vectors and get out another vector. So let's start with some notation. If I write I with a little hat over it, that's shorthand notation for the vector 1, 0, 0. That's a vector in R3. It's a unit vector of length 1. The vector j with a little hat over it will denote the vector 0, 1, 0. And the vector k with a hat 0, 0, 1. So this is a unit vector in the x direction, a unit vector in the y direction, and a unit vector in the z direction. All of these vectors are orthogonal, meaning they're all at 90-degree angles from one another. You could tell by taking the dot product of any two, and you get 0. One other piece of notation. If I write 4 numbers down and surround them with these straight bars, that means to take a 2 by 2 determinant. But really all this means is to do the calculation AD minus BC. So you multiply A times D, and then you subtract C times B. Okay, so let's introduce the cross product. Given two vectors, let's say I have the vector u, which is ABC, and the vector v, which is the vector xyz. The cross product is a really bizarre calculation at first. The cross product is denoted u cross v. And to calculate u cross v, I'm going to begin by drawing a 3 by 3 matrix, a 3 by 3 array of numbers and vectors. So in the top row, I'm going to write the vectors I hat, j hat, and k hat. In the second row, I'm going to write the entries in the vector u, so a, b, c. And then in the third row, I'm going to write the entries in the vector v. So I'm going to write x, y, z. Now here's what this means to do. I start in the top row. So I'm going to work along the top row here, moving left to right. I'm going to start with I hat. Now for the I hat term, I'm going to write down I hat times a certain number. And that number will be this determinant 2 by 2 calculation when I cross off the row and the column that contains I. So I'm going to cross off with my finger this column, and I'm going to cross off the top row, and I'm left with a 2 by 2 B, C, Y, Z. That will be the coefficient of I hat. Next, I'm going to subtract a similar calculation, but with j hat. So next I'm going to look at j hat. I'm going to cross off the row and the column that contains j hat. If I cross off that row and that column, I'm left with ACXZ. So I'm going to write that as a 2 by 2 determinant, ACXZ. And that'll be times j hat. And then the final calculation will be analogous for k hat. I'm going to cross off the row and the column that contains k hat, and I see A, B, X, Y times k hat. There, that's the calculation. It's a really crazy calculation. Why would anyone do this? Well, I'll show you in a minute. But first, let's do a numerical example. So let's take the cross product of 1 to 1 with 0, 3, 5. Okay, so you start by writing this thing down, I hat, j hat, k hat. The next row contains the numbers 1, 2, 1, and the last row 0, 3, 5. Okay, so what's the coefficient in front of I hat? So I hat has a coefficient in front. It's the 2 by 2 box that's left when I cross off the row and the column containing I hat. So I think I find 2, 1, 3, 5. The next entry, notice there's a minus sign only in this middle entry for some reason. But there's a minus sign here. Minus, now I'm going to cross off the row and the column containing j hat. I'm left with 1, 1, 0, 5, j hat. And then lastly, plus 1, 2, 0, 3, k hat. So I'll do the calculation. When you do this 2 by 2 determinant, you do the product of the diagonal entries, so 2 times 5 minus 3 times 1. So I'm going to get 10 minus 3. That'll be 7i. And I remember I is this unit vector 1, 0, 0. So I'll write that down here. Okay, the next determinant will be 1 times 5 minus 0. So 5 minus 0 gives me 5. J hat is 0, 1, 0. And lastly, this last determinant is 3. So 3 k hat is 0, 0, 1. So I end up with the vector 7, negative 5, 3. That's the cross product of these original two vectors. So that's how you take the cross product. But what is it doing for you? Why would you actually do the cross product? Here is the main theorem about why anyone cares about doing this really crazy calculation known as the cross product. So the theorem is, if I take the cross product of u and v, then I get a new vector. So I take the cross product of two vectors in R3, and I get a vector in R3. U cross v is orthogonal to both u and v. So this is the main purpose. The only reason anyone really cares about the cross product is because when you take the cross product, you get a vector out that is orthogonal at a 90-degree angle to both the two vectors you started with. So for instance, let's check that when we did this calculation, we actually did get a vector that's orthogonal to what we started with. How do you check orthogonal? In the last video, we showed that you see if you have orthogonal vectors by taking the dot product. If the dot product of two vectors is 0, then those vectors are at 90-degree angles, they're orthogonal. So let's see here. Let's do the dot product of 1, 2, 1 with 7, negative 5, 3. So I do the dot product and I get 7 minus 10 plus 3. Indeed, 0. So 1, 2, 1 and this vector are orthogonal. They're at 90-degree angles from one another. Let's do the second vector, 0, 3, 5. I'll take the dot product of that with 7, negative 5, 3. And I get 0 minus 15. So let me say 0 minus 15 plus 15. Again, getting 0. So in this video, what I did is introduce some strange notation and described how to calculate the cross product. You calculate the cross product doing this calculation, which honestly you have to do a few times on your own to get comfortable with. You got to get comfortable with the cross product. The cross product is giving you a vector that's perpendicular orthogonal at a right angle with the two vectors that you started with. Okay, in the next video we'll practice some more with cross products.